I'm David with EV World News. We're talking about electric vehicles, green energy, and the stock markets. And I'm back today with our founder and chief editor, Bill Moore, as well as some special guests today. I've got Rob Winston and Neil Winston from HopFlyt Aviation. And we love talking about aircraft on the show. So we're really happy to have you guys with us. How's it going today, Neil? Rob?
Hey, doing great.
Doing great.
All right.
Thanks for having us on.
No, I love it. So I ran into Neil at a conference in California, and I saw the thing, where, if I'm saying this right, it appears to be drone technology that's hauling cargo that's a lot heavier than an envelope.
Absolutely.
And I think I think I saw you could haul up to like 250 pounds, and you're specialized in maritime aviation. Is that correct?
Yes, that's correct.
So how did the maritime connection come into all of this?
Well, so we're developing this technology to have really a specific use case, and that's to move cargo in situations where otherwise it's very difficult to access, and where logistics are very complicated. And in an offshore or maritime situation, that's about as difficult and as expensive as you can get to move cargo. Yeah. Really, your only option in many cases is to deploy helicopters or small boats, both which burn massive amounts of fuel and are extremely costly to operate. Many helicopters, we're talking $4,000 to $5,000 an hour in pure operational costs, but very often in these situations, they need to move lightweight cargo, whether it's electrical components, mechanical components, or even things like mail and medical equipment. The only option is to deploy these helicopters. So by developing specialized aircraft that are designed to move a specific weight range of cargo in this light to medium weight category, you create an optimized solution and bring massive cost savings, really revolutionary cost savings, to missions that are otherwise relying on helicopters.
Well, if you're only moving, cargo that's say 100, 200 pounds, I mean, that's certainly a whole lot cheaper than, having, two people or whatever in a helicopter plus the cargo. I mean, that's a big reduction. I mean, what do you expect operating costs an hour for something like this to be?
Yeah, so it's really orders of magnitude lower. We're looking in ranges between $100 and $150 an hour,
wow.
accounting for maintenance and fuel. So it's really interesting, and it's a hybrid. It's based around a hybrid electric power plant. So in aviation, pure electric aviation just isn't quite there for these long range flights.
It doesn't have the range.
Technology can combine the best of both worlds, where you have these new electric aircraft configurations. But you still have the advantage in the range of a fuel-burning aircraft. So we're looking at the engine. The engine that we're deploying is a turbo generator that uses a recuperated fuel cycle, and it's been developed by our partner, UAV Turbines. They are a Miami-based company, and this engine burns under 3 gallons an hour. So in pure fuel costs, that's less than $15 an hour in fuel.
Yeah.
And then there's additional costs for operators, for maintenance, and we base these models and do life cycle cost analysis in ways that are very similar to what you'd expect with a turbine aircraft. So baking in a lot of those assumptions, we're in the range of about $100 to $150 an hour in operational costs.
What else is interesting is that the Navy has validated this need. The U.S. Navy has said more than whenever a ship at sea goes non-mission capable, 90% of the time is for a part that's 50 pounds or less.
Oh,
damn.
Hundreds of miles out of sea.
Yeah.
Now, they might have an H-60 on board, $5,000 an hour to go get a 50-pound part or less, a 10-pound part, say, and they might have, or they could deploy, if they deployed a CV-22 or a V-22, those are around $24,000.
Yeah.
So it's significant savings. So the Navy's looking for it. Offshore oil rigs are looking for this technology and other things also.
No, I mean, that just seems amazing. And what kind of range do one of these things have?
Yep. So the aircraft we're developing is called the Cyclone. And its nominal mission is 150 pounds of payload at a 500-mile radius.
Okay.
However, of course, with and performance calculations for any conventional aircraft or helicopter, you often look at a fuel to payload trade-off. So
right.
So with minimum payload that we're considering to be about 50 pounds, you then are pushing 800 plus miles of range and potentially over 12 hours of time in the air with this type of aircraft. And additionally, on the shorter end, a 250-pound payload with a 100-mile radius of operational use.
Okay. Yeah, what was I going to ask you on that regard? So what you've got at this point, what we've seen in the video there, that's your sort of your working prototype, which is, I think I read, it's like got like a 10-foot wingspan. What is the full scale model of this is what, somewhere around what, 27, 30 feet wingspan on it?
So it's what we're working towards is a 24-foot wingspan.
Okay.
As the full size vehicle, and that's at about a 800-pound maximum gross takeoff weight.
Okay. Now the fuel that you're using, is that kerosene, or are you using something else?
Yes, it's heavy fuels, somewhat agnostic. The ECU is adaptable, but it's going to be traditional kerosene or diesel, or their aviation analogies being Jet A or JP5 and JP8, like you see on military vessels.
Okay. So theoretically, this thing could have. Are you thinking? Well, I guess I was thinking, is that one way or round trip? Because obviously you can't leave it out there; it has to come back. So there's the possibility that it could fly 800 and then be refueled there on the vessel or the offshore, and then come back?
Yes, absolutely. So that's what really, and that's what gives these hybrid aircraft such an advantage compared to a pure electric aircraft, is that you don't really need infrastructure. You don't need special infrastructure beyond what's already existing on these platforms.
Right.
All you really need is fuel. The plans to build this aircraft, and with its turbo generator running, it can land, keep that turbine running until those batteries are topped off, which we're not talking large amounts of time. We're in the range of 30 kilowatts of power with that turbo generator. Charge those batteries up quickly and get off and get going fully fueled, and you'd have that maximum range available to you just with similar thought, and similar planning as a conventional aircraft.
Yeah, how big a battery pack are you looking at?
The overall mass of the battery pack is around 70 pounds.
Okay.
That's designed to give you about 5 minutes of hover time.
Okay.
Purely on battery. Translating that over into fixed wing flight time, then you're in the order of around 1 hour of maximum flight time on battery only.
Okay. And Mac, go ahead.
I'm sorry, Bill. And it recharges in flight, right? So that turbo generator recharges the battery. It's ready to top off. Another neat feature is this aircraft, if it was flown into an austere location, now you have a flying portable 30 kilowatt generator that you could run comms, you could, desalinate water, use it as a generator that can reach areas really fast.
Okay. So let's talk about, looks like Dave disappeared momentarily. Let's talk about the design. What you've got is, in a way, it's kind of a half ducted design that rotates. Yeah. So what's the advantage of doing that as opposed to maybe like just open blades like you see on so many like Archer and Beta, as opposed to ducted fans like what Airbus did on their original, ducted fan project 5 years ago?
Yeah. Absolutely.
I'll start off, and you could throw in, Neil, but it's a great question, because what is interesting is that is the difference in thrust between an open propeller and a closed propeller, right? In a duct. Right. So in a duct, you get the best static thrust, a total duct around it. And then but once you get over 60, 70 knots, now the drag from the duct negates any effect, right? Okay. So it's really great for static thrust. Now you have an open air propeller, and it's pretty, some of the major components of its thrust are how big is that propeller, and how
pitch
fast
of the
is it,
propeller.
right? The pitch of it and all that.
Yeah.
So, but now when you add a duct, and the duct was invented back in the late 40s, early 50s by the half duct by a man called Custer Willard. Very interesting.
Yeah.
And he tried to use it on a twin engine airplane. Imagine that your standard twin engine with these fixed ducts. Had all kinds of problems with it. But what the big advantage is with the engine, the propeller in the duct embedded in a half a duct, that duct is an airfoil. And when you pull air, it creates lift, or if you push air over, it creates lift. So you could create lift in a static situation. So as we hover, you can be a true powered lift aircraft that makes lift and thrust as you hover, instead of a helicopter that just does thrust, or a quadcopter that only does thrust. And then there's also advantage. If that propeller's turning, it never stalls. You can't really stall that duct unless maybe one situation if you moved it really fast, but still it's going to catch up and it's going to keep some air and create
is this a true VTOL? In other words, is it just like a helicopter straight up, or do you have to have some forward short takeoff and landing type approach, or is it or would you want to do one or the other?
So we can do both.
Yeah, it is a true VTOL aircraft, able to take off and land vertically, and what we call that propulsion arrangement with the propeller that's partially embedded in that semicircular airfoil. We call it a channel wing, and that's not a term that we coined. That was the term coined by the original inventor of that configuration, Willard Custer. He filed an original patent on that in, I believe, 1929. Built operational aircraft in the 40s and 50s. However, it ran into a lot of issues, but what we see is that the emergence of electric propulsion and modern digital control systems have solved a lot of the problems that were originally inherent to that design. So the channeling provides some distinct performance advantages because it augments the thrust produced by that propeller by creating lift. So we see about a 10% performance advantage in hover flight. However, what it also does is it unlocks a lot of really novel controls. So like Rob said, where those channel wings never stall, it enables really stable flight at just about any airspeed throughout transition. So you have stable and controllable flight because they can augment your control surfaces. So the control surfaces on the wings in that transition region, when it's going slowly, your control surfaces, whether they're elevators or ailerons, they're not super effective because you don't have a lot of airspeed.
Right.
So they can they can actuate and help those control surfaces and help keep the aircraft stable and controllable all throughout transition. And what you really create is an aircraft that's stable at any airspeed, and that translates into a lot of other performance characteristics, such as high wind recoveries, like you'd see often in a maritime environment, and also some novel controls, such as the ability to do very efficient recoveries through air braking and tuning specific approach profiles.
Okay.
So it's quite interesting, but the history of it is very fascinating, and I encourage you I encourage everyone to research the Willard Custer aircraft. They were very advanced aircraft, very advanced configurations, but what he ended up with was 2 of these channel wings. And the problem is that aircraft had such high performance, it was actually uncontrollable at low speed. It would take off at 17 knots. And we're talking about a 5,000-pound aircraft would take off with a 17-knot takeoff roll. That was just too slow for the elevators and the rudders to actuate.
Right.
Is tilting by actually, instead of having them fixed at an angle and trying to create a conventional aircraft, we can tilt them independently and provide really advanced control. And also some of the other problems was, he had massive 6-cylinder aircraft engines in these nacelles, creating a lot of extra drag. Electric motors get significantly smaller, so it solved a lot of the problems in terms of drag. And then we haven't quite talked about in fixed-wing flight, the aircraft flies very much like a traditional aircraft with traditional control surfaces. And those channel wings, while they have a slight drag penalty, they create so much additional lift that the actual overall lift-to-drag ratio is about the same as an aircraft with flat wings and normal propellers, because of that trade-off.
So if I understand correct, I have one of the little, hobby quadcopters, and I can change directions, vertical and horizontal axis and so on. And that's done by just slight shifts in the speed of the electric motors. So you can obviously do that with what you're doing, but I guess that you can also do that by independently shifting the rotation of the rotor itself. Is that what you're saying?
Yeah,
Yes, and
great.
it's really a combination of both of those. For example, if you wanted to swing the nose around, you can tilt them in opposite directions. And to move forward and backwards, you can keep the fuselage level by tilting those channel wings either forward or backwards as well. However, it can still do traditional pitch and roll through the use of differential thrust. And there's subtleties in the control system that also use the relative torques to help settle out where that nose is pointing.
Right. Okay. This sounds like you've got a lot of computer processing going on to make, not only from just controlling the attitude of the aircraft, but also from a navigation point of view, because there ain't no pilot on this thing.
Absolutely, and
Yeah.
not only
talk more about that.
Yeah, not only there's no pilot, but if there was a pilot, they wouldn't really be able to fly it in the first place. It's automated. It's automated down to the lowest level, so there's never really manual flight going on. Just like what you'd see with a quadcopter, where it's constantly computing its tilt angles, its attitude, and solving for that to make it as stable as possible, and that's throughout the entire flight. So really, when there's a pilot, and we operate it, I actually fly it fly our research aircraft during test missions, where I'm at least in the loop to take over. But we primarily do fully automated tests where we program in all the maneuvers, and there's really just a pilot in the loop to take over if they need to. But then that pilot is really just commanding rates. They're saying, okay, so I want it to slow down, I want it to speed up, I want it to move in this direction, but at the onboard flight computers really handling all of the actual inputs to get it to do what we want.
So you're what, flying in something like a Robinson or what? A heli? You're obviously not flying on a drone, so you're flying, I assume it's a helicopter nearby or fixed wing.
Oh, and so in most of our tests, it's all ground based and line of sight testing in our research. So we're often the aircraft's often within about a mile of the operator, such that it can be seen the whole time.
Let's go back to the genesis of this if we can. Maybe Rob, you can share with.
Sure.
I mean, how did this whole thing? You've got a long history. I think you've flown how many scores of different airplanes in your career? I mean, I've done maybe half a dozen, but it's like what, 160 or some wild number like that.
Go all the way back.
Yeah, not quite that many, but I've flown 42 different airplanes of different models and types of airplanes. I've had a great career in aviation, and I grew up. I was the only person in my family in aviation, and I was the kid that hung out at the airport. Started flying when I was 16. Was like, I really want to be a pilot, and kind of how my career progressed when I was a senior in college. This is when grant revenue budget cuts were going on, and they weren't going to be bringing in lots of pilots. So I got my first job. I was a test engineer for NASA at Johnson Space Center. Worked there a couple years, and then went back and got my master's degree and got in the Marine Corps and flew airplanes. And this is leading to your question. At the end of my career, I was asked by the admiral in charge of all the unmanned systems for the aviation systems for the Navy and the Marine Corps to take a look at, hey, let's do a strategic plan. Let's look at, future threats and what capabilities we need to bring online. And as I was doing that, I was like, we're really far behind in vertical takeoff and landing aircraft. We need a more efficient way of doing this.
Right.
So after I retired from the Marine Corps, I spent my career as a Marine Corps aviator and as testing airplanes, program manager duties and stuff like that. And when I retired, I started thinking about that. There's got to be a better way. So we worked many years and thinking about what is a much better way, that a more efficient way, because every VTOL aircraft is very, very power hungry. And what's a more efficient way of doing this? How can you fly farther, stay up longer, and stuff like that? And we began, doing the math, doing the engineering, the CAD work, and the simulations, and building smaller models and getting bigger and bigger. And we're working on our sixth patent right now, to patent protect this technology. And we're one of the few aviation companies that has a complete aircraft patent on how the configuration of the aircraft is, how it works, how it's controlled, which is very different. A lot of aviation patents that you'll see, they are, hey, we took an airplane and a regular airplane, we put lift motors on it, right?
Yeah.
And so they only can patent like, okay, we put, this is the differences that we did, but we have a complete aircraft patent and other little parts and pieces of that patent. And that's where it grew out. It's like, how can we help the military? And we were doing this even before the word EVTOL, electric vertical takeoff and landing, was coined, advanced air mobility, et cetera, trying to burn down the risk to move this forward. So it's been a great learning experience. And then also, I've also designed and built 4 other manned aircraft from scratch. So this was my first time to so it was a learning curve to get into actually the unmanned world. How do you build and design unmanned aircraft at a much smaller scale? So
yeah, I'm a member of the local EAA chapter, and me and several other guys are working on a Glass Star, I should say. So I'm learning how to buck rivets and things like that.
Yeah.
So,
yeah, and we'll have to have a beer and talk about airplanes, because I have helped build a Glass Air 1 RG, retractable gear Glass Air 1.
All right.
Way back in the mid 80s. So that was one of the airplanes I've worked on, but I've helped build about a dozen different experimentals.
Okay. Well, this is my first one, so. Mm-hmm. But I was explaining this. My dad, between graduating from high school in 1945 and going into the Army, that fall, he worked over here at Bellevue on the Boeing B-29. That was when they were turning those out. And so he was bucking rivets as a teenager. And so I'm just I'm picking up where my dad left
That's
off
awesome.
and seeing what it's like to actually build, an airplane out of aluminum and all the other pieces that go into it. So let's talk a little. So this is ultimately going to be an autonomous operation. We're just, you've got to deliver some parts for a compressor or something on an offshore rig, or they need to restock their medical supplies. And so it's going to go out there. Is there going to be pilot intervention back, in Houston somewhere where you're controlling it remotely, or is it going to be completely autonomous, fly out to the rig, settle on the helipad, and then return? So maybe give us a little sense of what you envision there.
Yeah. So that it will be autonomous, but this is a little bit of the challenge with the term autonomous, where it's a little bit of a buzzword, and it can mean slightly different things. So the idea is, yes, it's a fully autonomous aircraft that will that is designed to take off, fly the entire mission, and land without human intervention. However, regulation will drive humans in the loop. So there will always be a ground-based monitoring pilot who's monitoring aircraft states throughout. And in the event of an anomaly, they would be able to take over and make decisions on behalf of the aircraft, or perhaps even manually manually fly or manually recover the aircraft. In an offshore setting, we imagine a situation where it takes off from a port and flies to an offshore rig. That situation is going to have two operators actually in the loop. There'll be the ground-based operator on the shore who will inspect the aircraft and monitor it on the first half of that flight. There will be a handoff in between, and then the embarked operator, who's either on a platform or on a ship, will hand off control, and they will bring it in the rest of the way and up to the point of the landing. And they'll be a visual observer, visually watching the aircraft coming in, down, and landing. Being one of the most critical phases of flight, they'll have the decision to either wave it off and allow it to try again. And these sorts of operational models, they align with how we expect the regulation to look. The regulation isn't quite there for this technology yet, but that's how we expect the regulation to look. And it's modeled similarly to how the military does unmanned aircraft operations already. But in this offshore environment, one of the reasons we're targeting it is not only are they does it make sense from the requirement for not only does it make sense in that in an offshore setting, helicopters are really the only option, and there's a big cost argument, but there's also a big regulatory argument for why why it makes sense for this technology to begin in an offshore setting, because we expect regulation to be risk-based and certification to be risk-based to allow operation. So flying over open water is about as low risk as you can get, and that's certainly going to be much easier to begin doing before you're able to fly these aircraft, say, over busy or an urban area. So from a regulatory perspective, it's some of the lowest risk to initiate operations in this environment as well.
That makes a lot of sense. I've been trying to think. So if you're communicating like with a cruise ship that's out at, now they're never that far out at sea or whatever, but still you're communicating with it, and it probably has some type of helipad or something where it could land possibly, but they would have some, besides that operator, they probably have some type of software communication with you guys that helps bring in the drone.
Yes. So the way that this would work in terms of the making sure that it lands, that it has a safe approach and a safe landing, is going to depend on a couple backup systems. One, of course, is the operator who's actually there physically monitoring and watching the aircraft, because these are going to be expensive aircraft. About the 800-pound autonomous aircraft that can fly that far, we're talking about $2 million. So certainly you don't want, these are not going to be disposable from a commercial standpoint. So there's going to be an operator. However, the aircraft, in order to do its autonomous functions, it's going to come in and recover on what is essentially a pre-surveyed landing area. So it's the intention is not have it immediately landing on ships that it's never been to before or that nobody's ever surveyed. So part of that process involves figuring out the dimensions, say the height of that helipad above the water, and then there's actually going to be the placement of a couple antennas around that helipad. Those will be GPS antennas to help the aircraft do a differential GPS landing. So the aircraft knows its position and it knows the GPS satellites it's looking at, and then the ground, and then here on the ground, it's also looking at those same GPS satellites. And what it's able to do is figure out its position relative to the landing pad to extremely high levels of accuracy. We're talking about centimeter level accuracy, and automatically recover to that landing pad using its knowledge about where it is relative to the landing pad. There's additional backup systems such as the use of LiDAR to back up your calculations and bring it in as well. But really, the core of the recovery will be based on the use of GPS.
Okay.
Nice.
How much of this have you been able to? Is this still in this is what we want to have happen, and how much of this has you gotten? We've got you the 10-foot prototype flying. Where are you at in the progression of getting to these different advanced capabilities?
Yes, so we currently have two 10-foot wingspan research aircraft. They use the same configuration, but they're about 40% scale from that aircraft that will be 24-foot
Right.
wingspan.
Right.
So they've been used for flight controls development and for performance research. So the first steps are making sure that we have the controls locked down, and that it's flying the way that we expect, and that it's that it's responding to commands appropriately, and that it's able to. Then the kind of culmination of flight controls development is being able to do fully autonomous flights, from takeoff to transition to fixed wing flight, fly waypoints, come back, recover, all without human input. Now, those flights we've all done using what we call it's using differential GPS, but what in industry is often called RTK, or a real-time kinematic solution. So that's been done autonomously using differential GPS, but of course all shore-based, and we haven't got these aircraft out at sea. The next step that we're currently flight testing through the summer is performance research. So we have initial performance models that allow us to do hybrid system design, because in hybrid system you have to have a really good understanding of how much energy the aircraft requires in order to design those flight profiles. So we're continuing performance research this summer with our second research aircraft to characterize how much power, draw, and build our models. So that's going to ultimately driving the final configuration that we're developing for the Cyclone aircraft. Simultaneously, we've been forming partnerships, and we have our partnership with UAV Turbines, which is a Miami-based turbo generator manufacturer, and they've created the engine that we will be flying on the Cyclone. It's a 30 kilowatt turbo generator that uses an advanced recuperated fuel cycle. So it actually recycles the exhaust gas to preheat fuel and bring down the and create a highly efficient engine. And we similarly have formed manufacturing partnerships with an Indianapolis-based company, Aerodyne Composites, who got their start in motorsports, building IndyCar chassis and race car components, and has moved into aerospace over the past 15 years. And they're our other partner in manufacturing. So we're going through advanced design stages at the moment to settle on the final configuration for this large hybrid electric aircraft.
Okay. So right now, the 10-foot model is, I assume, that doesn't have a turbine mounted in it. You're operating basically on battery power at this time. Right?
Those are fully electric aircraft. Yep.
Right. Okay. All right. Cybersecurity. Keeping my eye on what's going on in Ukraine with the drones and the scrambling of GPS signals and all that stuff that's going on. So, I could see this going out, into the Gulf of Mexico and servicing oil platforms, or, delivering supplies for some, to a cruise ship or whatever. I can also see, knowing that drug cartels have built their own submarines. So right. What are your thoughts in terms of how do you keep this out of the wrong hands, either by hijacking it electronically, or what are those ramifications?
Yeah, absolutely. So that, we're obviously in development for a commercial use case. While the core of our development is based around a commercial use case, obviously this is dual use technology that has strong applications in military and defense, and needs to be hardened against things like GPS spoofing, right, or GPS jamming. So you need to have backup. You need to have backup communications, whether it's and the level of that hardening looks different for commercial aircraft. Will look different for commercial aircraft versus a military aircraft, just by pure nature of where they'll be operating. However, there are in purely a commercial aircraft, there will be backup systems for GPS for the event that GPS becomes unavailable to safely navigate the aircraft back. We recently signed an MOU with a autonomous navigation company who's using machine learning and artificial intelligence to provide GPS denied navigation services.
Okay.
And that's important, not only because not only for the dual use military technology, but just in the case that GPS becomes unavailable, because it can't be your only source of navigation data in any case, because And I have a background in GPS-based flight testing. Before I was here for HopFlyt, I was the lead certification engineer for shipboard precision landing systems used by the F-35. And
okay.
And it was based around the use of differential GPS navigate. Its core landing system is based around the use of differential GPS to provide precision data. So there's always these thoughts of, okay, what are your backups? What do you need to do in the case that GPS becomes unavailable? And what is that? What are those procedures, and everything from procedures to your hardware requirements?
Okay. Can we talk a little bit about your business model? Are you guys going to manufacture and have leasing companies or oil service companies or whatever acquire these from you, and you provide support service or whatever? What's that model look like?
Yeah, that's a great question, because Morgan Stanley has humongous total addressable market on this technology, billions up to trillions of dollars a year. And one of the things that we're looking at several different models. We have a licensing model. We have other companies license our technology. We have models. So we're doing that. We also have some letters of intent to buy aircraft, right? Straight out buy aircraft. Both our smaller and our larger aircraft. And also there's also the model that you own the aircraft and you lease it, which would take a larger staff to do that, because then you have to get the operators up and stuff like that. But one of the other models is you sell it, but you keep the maintenance, right? The maintenance piece and the training piece going for the companies, the upgrades to the aircraft, et cetera. But there's a lot of very interesting ways of slicing and dicing it. But I tell you what our core group loves here at HopFlyt, we like the conceptual design. Neil and I are both testers. We like testing and prototyping. So with our manufacturing partners, like Neil said, Aerodyne Composites, they're going to be making the airframe. We'll do final assembly. Then we have another partner called SRS Robotics that helps with the electronics and et cetera. Once you get the airframe back, build the electronics and payloads integrations and stuff like that. There is, as you know, from building your Glass Star, there's a lot of touch labor on an airplane, right?
Oh, yeah, a lot.
So getting those designed for manufacturing, reducing that touch labor, letting our partners do a piece here, another partner doing a piece here, it makes us it's a force multiplier, right? That's just what's wonderful about working in the economy. We're doing all the Cyclone that we're building, all USA. You trying to shoot for all U.S. made components, having a bunch of small companies work together and be able to perform like a large company to penetrate, the dual use military and civilian markets.
Yeah, and if I'd say, and if we and thinking about customer base, at least in a commercial sense, the targeted customers are the current users of helicopters, and in an offshore setting, that's not often the oil and gas companies. They don't often own large fleets of their own helicopters. Rather, they have services provided by leasing companies.
Right.
So they're really in the commercial world. It's these helicopter leasing companies that immediately realize the value and cost savings, and they understand the rates of utilization for these helicopters, particularly how often they are ferrying cargo versus ferrying passengers versus performing search and rescue or other types of missions. And there's been strong traction in this industry already, and strong interest from helicopter leasing companies. Because when we look at the overall operational cost savings, and with aircraft ownership, the value is really in life cycle cost of an aircraft, because otherwise it's big numbers, it's big operational costs, expenses to purchase, but the value is realized over the long term. And we've ran that in comparison to modern offshore helicopters. And with a hybrid electric platform like this, under the normal rates of utilization, so for an aircraft that's around 300 hours per year. So for every 300 hours per year that this cyclone can replace in missions that were otherwise conducted by helicopters, that's $1 million in pure operational cost savings realized by a helicopter services company. So, a single aircraft can bring an operator $1 million per year. So with those cost savings and at a $2 million aircraft, it almost pays for itself in 2 years in just pure operational costs alone.
And additionally, it frees up those manned helicopters to do the manned missions, to do those, carrying people, passengers, very large cargo, whatever else needs to do. So it doubly would help a helicopter leasing company.
Yeah, and helicopters are in fairly high demand, and they're of course large and complex aircraft. So they're slow to manufacture, and there's a backlog of helicopters worldwide. So the demand for helicopters is already very high. So it's just attractive for these companies to free up helicopters to do things that they're better optimized for.
Right.
In additionally to being able to diversify their fleets, with global supply chains, and often helicopter in aerospace, they're somewhat global supply chains, but there's many situations that could ground entire fleets of helicopters. So operators are looking to diversify their fleets to not be put in that situation. Yeah. Think about a country like Norway that relies on helicopters for their energy sector.
Right.
That's critical infrastructure, and they can't, if they have a fleet of all the same, say, Airbus helicopter, and there becomes a maintenance supply chain issue, that could ground an entire fleet and shut down, some of their most critical industries and critical infrastructure.
Yeah. Hey, can you talk a little bit about the flight profile here? What are these going to be operating? Assuming you got a range of 100 to 800 miles. Typically, what's the flight profile? You're going to be operating at 100 feet. You're going to be operating at 5,000 feet, or is that all going to be dictated by FAA? And then once you get outside territorial waters, what happens?
Yeah, so we're going to really see the FAA or regulators will drive the altitudes that these aircraft are allowed to operate at, and so we don't really know where they will be mandated to fly. We'd expect that initially, and with the way that regulation currently sits, it is the use of a corridor and a defined altitude and defined airspace that the aircraft is allowed to stay within. So that's often low altitude, very often less than 5,000 feet for unmanned aircraft. Now, when we design these aircraft, they are optimized around 15,000 feet. That's our with the engine data, all optimization is just about optimization is happening around 15,000 density altitude.
Right.
However, regulation will drive it. Now, when you get out into international waters, it depends, because there's levels of control that the government still has or mandates in terms of restricted ranges. So that also depends, because many there still might be rules or desires to keep them at low altitude still there in those ranges. It's really such an emerging environment. We'll have to see how this how the regulation plays out. Yeah. And I expect us to have some answers on that regulation in just the next few months.
Because I would think there'd be some kind of national security issues here too. Is that you want to be able to have, assuming you're going to have transponders or something on the aircraft, and it's going to have to operate at a specific altitude, so radar, can see it. So we have we don't want somebody coming in with a payload that we don't want to have coming in, right? And not know about it. Which brings up the question, now that I think about this, are your drones the ones that we're seeing over New Jersey?
We can't confirm or deny that.
Well, we're fairly close. We're here on the eastern shore of Maryland, so we've got this coastal region just south of New Jersey covered. I'd like to say that it was us, but unfortunately, I think I personally chalk that up to mostly a mass hysteria situation.
Okay, all right.
Yeah. So you have an investor section on your website. Curious, how much money have you guys had? What, if you don't mind, I don't want to get too deep if you can't reveal this, but I'm curious what kind of money has been put in this so far to get to where y'all are at.
Yeah, so we've been very fortunate. I'll just give you some more history of HopFlyt. So instead of living at your normal house with a garage, I live on a flying community with a 5,000 square foot hangar attached to my house. So we started HopFlyt right there in that hangar. We had composite shops. We had, metalworking, offices, everything right there in the hangar, and hangar space to build, places to fly, and stuff like that. So we've started with virtually no overhead and did that for years. So we only did a few friends and family raises. And the only reason I'm not going to go into tons of detail, because we're doing a raise that we can't officially advertise, right? So I'm not going to go into lots of details about that, because that's.
Have you not filed the Reg D or Reg A or whatever you're doing?
Yeah, we filed all the required paperwork, but we're doing a regulation 506B. You only can advertise a C, so we're doing a B, but we are doing a raise, and but we did friends and family raises, and it's been extremely frugal with our money to get where we are, because you will literally see companies have raised hundreds and hundreds of millions of dollars, and we're flying autonomous aircraft. We're all the way a whole unique design in autonomous aircraft, and what we've done on a shoestring budget,
and fully built and fully in-house built,
fully in-house.
With all the our small team did all of the composite manufacturing in-house, developed brand new methods to create tooling, to create the molds for the fuselages, it really innovating advanced prototyping methods. We built composite molds with large homemade 3D printers to build mold sections, building entire mold. These are 5 foot tall molds made over the course of about 2 weeks with multiple 3D printers continuously running, to then and figuring out, okay, the processes, with really talented engineers involved, with deep backgrounds in material science and composite manufacturing, to say, okay, let's make some new, let's create new processes to do composite layups on these molds that we've 3D printed, to create our fuselages, and refine that over time. But very, very low material costs ultimately to get to this point.
Cool. Sounds like a Burt Rutan type project then.
Yeah, but we are you can see behind us, we've got a wonderful place here in the eastern shore of Maryland, and we're accelerating now. We're moving on, and we'll be and you'll be hearing more about us. We'll keep you up to date when we switch over our raise, where we can officially talk about it in a wide audience.
When do you anticipate mating the turbine?
That's going to be about a 12-month prior to 12 months, but we're anticipating initial flight tests of that aircraft, the very first hovers, and ground testing at the beginning of next summer. So the integration of that turbine is planned mid-spring, and moving into ground testing and flight testing next summer.
Great. Dave?
Hi, I think we're pretty good. And we've ran a long time. We've almost gone 50 minutes. Rob, Neil, I want to thank you guys for coming on today. Folks, I want to thank everybody for listening to us. Bill and I have a tendency to just ramble on our own, so it's nice to have some other people to ramble on with us.
Keep us focused.
Yeah, keep us focused. Yeah. I'm going to go ahead and end the show. Just hang out with us for a minute.